Do you get it? Kind of abstract. Who gets it? Let's piece it together for those of you guys who get it. So we got f of x, and it's a continuous function. It's continuous at every point of AB and differentiable at every point open AB. So we've got an A, f of A. We've got a B, f of B. Nothing's guaranteed about whether f of A or f of B or one's higher than the other or vice versa, right? We don't know. All we know is that this function is continuous and differentiable, and differentiable involves being smooth and continuous, okay? So it's smooth and continuous on this interval. Let's draw an example. All right. Then there is at least one point C in AB where f prime of C equals f of B minus f of A over B minus A. Let's break it down. What's f of B minus f of A over B minus A? Those of you who are understanding what this means, help me through it. Cole.
It's the slope of the line that intersects those 2 points.
Okay, so if I were to draw a secant line here, isn't the slope of that line f of B minus f of A over B minus A? I don't care where the 2 points are. All year long, the slope between 2 points has been f of B minus f of A over B minus A ever since algebra 1. Yes? Slope of that blue line. Awesome. That's this part. What's this part? We'll go to Cole if nobody else saw first. Tom.
The slope of a point in between.
Mm-hmm. Good. Specifically, where? So I'm going to put C here. I'm not saying this is correct. I'm going to put C in purple.
Looks like green.
It does look like green. I said purple. Thank you. I'm going to put C there. But C, where's C? There is at least one point C in AB. Ready? Shh. Where am I? Where am I? Where am I? Not anywhere. It can't be anywhere. It has to be the x value, the C value, where the slope at C equals the slope of that blue segment. Do you see it? Cool.
Just past the match to the next.
Over here?
Mm-hmm.
So here we go. Are you ready? Isn't this a tangent slope? That's the slope at a point C. Yes? It has to equal the secant slope. So I'm just going to draw a little tangent segment right here, because this is the slope it has to match. Do you guys agree? Now let's do the little slope thing. It could be there. That's possible. Ready? There. And there. And there. How do I know there has to be at least one of those little C values somewhere in this region here? Somewhere in this region right here, between here and here. Because the slopes go from negative to positive. Steep negative, not so steep negative, zero slope, positive slope. And I think we would all agree, this blue slope looks negative. Looks negative. Because f of B is lower than f of A. Okay. So, one of these C values has to be there. Let's keep going. Nope. No. Yes. You agree? C2. Another C value where the instantaneous slope equaled that average slope. You follow me? Okay. This is a huge theorem. Put stars next to this. It's the mean value theorem. Mean value theorem. The real MVT. MVT. The mean value theorem. And as you know, I like to give real life examples so it sticks in your mind. Oh yeah, that was the temperature. No, the temperature example was the intermediate value theorem. Oh, the temperature to start the day was 36. The temperature to finish the day was 53. The temperature must be every single degree and tenth of a degree and hundredth of a degree between 36 and 53. Agreed? Intermediate value theorem. This is the mean value theorem. Mean meaning average. Okay? Mean is an average. It's an average slope. The blue is the average slope. The red is an instantaneous slope. Here we go. We're taking a field trip on the turnpike. Okay? Unfortunately, Cole isn't here today. That Cole. Adam has had the privilege of driving with me on the microbreak. It's classic, isn't it? Good times when we drive together on the school bus. I got my van permits. I drive the team. That's right. It's awesome. Now, we're taking a field trip, and I'm taking all of you. Even though we can only fit 9 in there, I'm taking all of you, okay? We're going to go to the turnpike up on Route 8, and we pull up to the first toll booth. And when you first get on the turnpike, you get a ticket, right? You pull out the ticket, you start driving on the turnpike, all right? And we're cruising. I mean, we're having a blast. Music's blaring. What are we listening to?
Pardon the USA.
Huh?
Pardon the USA.
Pardon the USA. Taylor Swift? No. What is
Cyrus.
that? Thank you. I'm not good with teeny pop music. All right. Miley Cyrus, Hannah Montana. All right. Whoever it is. We're cruising. I lose track of the speed. I apologize. I start speeding. Okay. The speed limit was 70, by the way. And we drove for an hour. Okay. We pull up to the next toll booth. Man, this is gonna stick in your mind. Oh, those good times we were cruising the part of the USA. I'll dance in beat and tune together. I don't know. Snacks. Probably have snacks even though we're not allowed. We're making this up, so we get to do it. All right, we go to the next toll booth. We pull up, we slow down, we stop. I hand the toll booth worker my ticket and the money. And they say, I'm sorry to say, but you just drove for 1 hour and you drove 80 miles. You must have been speeding because your average speed was 80 miles per hour. You just drove 80 miles in that last hour. The speed limit was 70. I'm going to have to write you a ticket. Mathematically fair? Mathematically fair. Is there any way I could have not been speeding? No, I had to be going over 70 at least 1 point. Are you ready? Let's change the story. We drove 70 miles in 1 hour, and the speed limit was 70. And they say, I'm still writing the ticket. You were speeding. True? Fair? Not fair.
Possibly.
Who votes not fair? Who votes fair?
Possibly.
Listen to the whole story. Listen to the whole story. I was stopped at the toll booth, and I grabbed the ticket.
Oh my God.
And then you didn't listen to the story. You were jamming out to Miley Cyrus. You weren't listening. All right, we start driving, and then we slow down to the next toll booth, and we hand them the ticket. What did we do?
We went over 70.
We went over 70 at least once because our average was 70, and we were stopped and then going whatever, and then stopped again. We must, if we were averaging 70, we must have gone over 70 at least once. You agree? Our our instantaneous rate of change equaled our average rate of change at least once.
It's actually
I don't know if they're allowed to do that.
It's like that.
Lizzie is asking the same. I don't know. I don't. Is it fair though? Would it be fair?
Probably.
Yes. Fair? Yes. Cool? No.
Yeah.
All right. Does that make sense? That's the mean value theorem. If you want to write yourself a little note saying toll booth example, you're welcome to. You are going to have to cite this example on the AP test in the extended response portion. You're going to have to literally say, by the MVT, there must be one value where the instantaneous rate of change equals the average. Does that make sense? Does the example make sense? Now, what if the hypothesis is not met? And remember, the hypothesis is everything before the then. Okay? Everything before the then. Okay, let's give an example where f of x is continuous, but not differentiable. I'm going to try to make this a little more obvious. Does the MVT apply? What's the slope? What's the average slope? What's the f of b minus f of a over b minus a? 0. Is there an instantaneous rate of change of 0? Positive, 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 positive. Really positive. Doesn't exist. Ouch. Negative, 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 negative. Did it ever equal 0? So the mean value theorem only applies if the hypothesis is, that was going to be wrong. I stopped. I had to catch myself there. The mean value theorem is only guaranteed to apply if the hypothesis is met. Could it still apply? It could. It could. You want an example? Taking a deep dive here. What's the average rate of change on this interval? 0. Yes? Does the mean value theorem apply? Ooh, careful. It does. Let me back up. Is the hypothesis of the mean value theorem met? No. This is not continuous. It is not differentiable. Could the conclusion still apply? Is there ever an instantaneous rate of change of 0? Boom. Boom. Possibly. Boom. Yes?
Yeah.
All right. So if it asks, is the mean value theorem, is the hypothesis met, you say no and you stop the problem. All right. You just say no. Stop the problem. All right. That was just a taste. Do you have any homework questions for me from the weekend? We need to wrap up 4-1. Okay. And here's why I'm okay with leaving 4-1 and moving on for now, is that we've spent several days on it. You have the videos. You have the process down. I would probably venture to say the only thing you're struggling with at this point in that process is probably the algebra of it. Like, I could take the derivative. Can I set it equal to 0? It's kind of tricky. Or can I find the domain of it? Oh, that's pre-calc, right? Algebra 2, pre-calc, domain. But taking the derivative, you should be fine with. Yes? And so reason 2, I'm okay with leaving it behind for a little bit, is it coming up in section 4.3, we're going to be doing what's called the second derivative test. So we're going to take the derivative and take a second derivative and do this process all over again with the second derivative. So we're going to be practicing this more. Plus, you guys are going to forget a bunch of stuff over break anyway.
Yeah,
So we'll cycle back through and review a little bit later. Any questions you'd like to see worked out or discussed from the homework, Madison? Yep. 26. That was the one over the cube root one? Was it 1 minus x squared, I believe?
Yes.
All right, and the question was to find the extreme values of the function. I would avoid the quotient rule. I would write this as a negative exponent. So step 1. All right, I would hate it. I would really hate it if you subtract 1 from the exponent and you subtract incorrectly. You're subtracting 3/3, so now you have the negative 4/3 power. Good? All right, so we have a positive 2x over a 3 times 1 minus x squared to the 4/3. And this is where, like, I'm just warning you, I am very careful when I'm taking derivatives. I'm very careful when I'm rewriting it. I double check this step. Because if you get this step wrong, you're in trouble. So a negative, a positive. The 2x stays up top. The 3's already down there. This gets dropped down. Good to go. Madison, you good? Step 2. The only time a fraction equals 0 is when its numerator equals 0. So x equals 0 is a critical point. And I broke my own rule already. I need to find the domain. Find the domain of the original. Okay. Can 1 minus x squared be negative? Can the inside of a cube root be negative? Can the inside of a cube root be negative? I hear no. I see some yeses. I see some confused, perplexed looks. What's the cube root of 8? 2. What's the cube root of negative 8? Yes? Negative 2 times negative 2? 4. Times negative 2? Negative 8. Cube root of negative 8 is negative 2. Can the inside of a cube root be negative? You can. So for this domain, we're not setting 1 minus x squared greater than 0. The only issue is when that 1 minus x squared equals 0. Do you agree? The denominator cannot be 0. Okay? And for domain, I'm not going to write it yet. I'm going to say 1 minus x squared cannot equal 0. Okay? So what does 1 minus x squared look like? 1 minus x squared. Do you agree? Now, this is not a between or beyond interval domain. It's points where it doesn't exist. What are those points? When does, if 1 minus x squared can equal 0, the question is when does 1 minus x squared equal 0? Negative 1 and 1. Agreed? Negative 1 and 1. So what's my domain? I mean, I don't know if you really want to write negative infinity to negative 1, parenthesis, 1 to, negative 1 to 1, parenthesis, union, 1 to infinity. I'd be okay if you put all real where x does not equal -1 or +1. That's kind of unclear. Do you guys understand? That's all real except where x equals -1 or +1. I didn't say it very clearly. I apologize. Okay, so does 0 count? Is 0 a critical point? Yeah, no issues there. Step 3. When does the derivative fail to exist? Well, here's the derivative. When does it fail to exist? One and -1, right? Are we going to count those towards critical points? No. They're not on the domain of y. They're not going to be a critical point of y. They're not going to be a max or a min because they don't exist. Do you agree? On to step 4. Any endpoints? Not really. 5, test. All right, x equals 0 is our only critical point. X equals -1 and x equals +1. I'm going to put on my number line. Why do you think that? Why do you think I'm going to put them on the number line? Max?
So then you don't use them as test points.
I don't use them as test points. That's a great answer. And they could be boundary points of where regions change sign. If there's an asymptote there, I want to at least know what's happening before and after those points. Do you agree? Okay. So I'm going to call them, if you want to call them critical points, that's fine. It is where the derivative, I guess, failed to exist. But they're not going to count as maximums or minimums. Okay. So I'm going to put myself a note. Not on y. Not on y. So let's test before. -2 is a test point. Let's test between. Something I would caution you guys, a lot of you are not drawing out all the steps, and you might be like, I'm good, I don't need to do that. Be careful, all right? 2, the next thing, we need to practice justifying our answers using calculus, all right? Justifying our answers. So we'll talk about that here in a minute. All right, we're plugging these into f prime. No matter what I plug in, other than 1 or -1, what's the result going to be after I do 1 minus x squared and then I take it to the 4/3 power? Positive. Because think about it. Aren't I cube rooting it and then raising it to the 4th? Okay, cube rooting it could be negative. Raise it to the 4th, positive. So I'm not even going to consider my denominator. I just know that it's going to be positive in the denominator, right? So let's plug these into the numerator. When I plug in -2, I get a negative derivative. Negative numerator, positive denominator, right? Plug in -1/2. Negative. Okay, let's take a minute. my f of x must have been decreasing and then got to this weird not on domain point, and then what afterwards? Kept decreasing. So even though that point wasn't even going to be considered as an extrema, it's still good to know what was happening around it. All right. Plug in a half. What do you get? Positive or negative derivative? Positive, which means f is increasing. And then plug in 2. Positive forever. All right, our only critical point was 0. F prime changed from negative to positive. That means F went from decreasing to increasing. At a smooth critical point, that must be a minimum. Okay, minimum. And let's plug it back into the original to get the y value. I'm getting 1, 0, 1. Did you graph it, Madison? I don't remember. Let's take a look at the original. Let's use our skills from first 2 weeks of school. When you plug in 1 into the original, what do you get? 1 over 0. What do we expect to probably be happening there? 1 over 0. Work last asymptote. What kind of vertical asymptote do you come from the left and you're decreasing, and then from the right? From the left decreasing and then pick up after it and still decrease. Yes? Let's check it. 1 over the cube root of 4 minus x squared. Let me draw it again. So decreasing, I don't know where, and then do you agree? Decreasing, decreasing. Yes? Possible. I haven't looked at this one, to be honest. 1 over the cube root. You have a syntax error. Oh, stop it. One minus x squared. That's it, right? Original. Okay. So it goes down and then picks up, reaches its minimum, goes up, and then increases. Do you agree? Now, how many of you would have looked at it and said, man, I know this is extremely boring for a lot of you. Would you guys rather go slope intercept form? I'm guessing from the looks on your faces as I teach these lessons, you're like, this is terrible and extremely boring and tedious. Okay. That's like my wheelhouse, okay? Nah, it's terrible. I'm a terrible person. But things like this, I find like interesting. How many of you would have looked at that and said, absolute minimum at that critical point? Come on, did you get that far? How many of you would have looked at this and said, okay, decreasing, min, increasing, oh, that's the lowest point on the graph. Come on. It's the only critical point. Decreasing from the left, increasing to the right, minimum. Absolute minimum. But first couple chapters, does this have any horizontal asymptotes? As x goes to infinity, a billion, a trillion, a quadrillion. What's this getting close to? 1 over a huge number. Yes? 0. Negative infinity. 0. If 0 is a horizontal asymptote, and that's the end behavior model, and my critical point was at 0, 1, above that, that's not the lowest point of the graph. Kind of have to pair this with end behavior models to really think about that. Okay? I'm not going to do that to you on a quiz. Madison? You happy with that one?
Yeah.
Maybe not happy, but at that point, we were going to classify it as a local. Kind of a mean one. That's how I roll. All right, we're going to do an example of the mean value theorem. Show that the function f of x equals x squared satisfies the hypothesis of the mean value theorem on the interval from 0 to 2. Then find a solution C to the equation. So there's the mean value theorem in theory, which is the toll booth example. Then there's the mean value theorem in practice that says, show me where that time occurs. All right. We're starting off with a very easy one. First of all, f of x equals x squared. Is x squared continuous on any interval? On all intervals. Yes. Is it smooth on all intervals? Yes. So is the hypothesis met? Yes. On a quiz, you're going to be asked, does the hypothesis apply for this problem? Yes or no? Circle yes on this one. All right. If so, find the value of C that is guaranteed by the mean value theorem. So we have two parts to this. We have f prime of C, and we have f of B minus f of A over B minus A. And you're given the interval, A is 0, B is 2. So we're going to do f of 2 minus f of 0 over 2. Let's do that part first. What's f of 2? 4. Minus 0?
4.
Over 2. 2. 2 is our what? Average rate of change. Slope. Slope of 2. Connecting A, f of A, and B, f of B. Now for the left part. What's f prime of C? What? I'm going to be mean here. 2C. F prime of x is 2x. F prime of C is 2C. So guess what the mean value theorem's conclusion says? Where are these equal? So I'm going to set 2C equal to 2. Not that exciting. Where is it?
1.
C equals 1. At C equals 1, the instantaneous rate of change equals the average rate of change on the interval. What would you do if you got a point outside of your interval? Like, what if you had to solve a square root problem and you got plus or minus 1? Ignore the negative if it's a positive interval, right? Just apply the positive answer of it, the one that's on the interval. Make sense? All right. We're going to have some MVT problems for tonight. But to get us thinking about tomorrow, if I ask you to tell me the interval where a function is increasing or decreasing, what are you looking for? A function is increasing when its slopes are positive. So it's like taking that number line test. And wherever we put a plus, it's that interval. That's tomorrow. Easy. All right, let me double check the homework. 3, 6, 9. 15. It's Amazon Music. All right, I'm going to change this up a bit. So there's a couple extrema problems in the homework. I'm going to put mostly. So before you write this down, I'm going to say 1 through 3. 1 through 3. 1 through 3 and 6 are mean value theorem questions. 9 is practice writing a secant line and a tangent line. And then 15, 18, 21 are local extrema questions. All right? Just a good variety for tonight. Thank you, Adam.